Welcome back to the channel. We'll be doing some more statistics today and working on Unit 8, 9. Unit 9 sampling distributions. And if you haven't watched the last video, we did a lot of work within Unit 9. And sampling distributions are basically probability distributions for the possible values a statistic can take. And a statistic is a measure of a sample. I'm talking really weird this morning, but yep, so it's basically the probability distribution of all the possible values a sample could take. One sample can take statistic. Oh my goodness. Anyways, let's just quickly read this again. Okay. Bridges the gap between theoretical probability and practical statistics. This is where students learn one of the most profound insights in statistics. Even if individual measurements are highly variable, averages and proportions from samples follow predictable patterns. So individual measurements from samples, those are what statistics are. And when sample sizes are large enough, not number of samples, but sample sizes, so how big each sample is, sampling distributions will have a tendency to fall into a normal distribution, which has a lot of properties. And the reason for this is because of the central limit theorem. We haven't discussed the proof for it, but it just works. But they only work under certain assumptions. So that's a really core part. It doesn't just always work. So it has to do with the expected value for fails and successes within your samples. And it also has to do with the sample size, as I mentioned. But to make this video just a bit different, I want to go ahead and watch the end of my last video, the recap, just to hear myself talk about what we discussed in the last video. This. We talked about okay, so for Unit 9, the past 2 hours, it's pretty weird to hear myself talk, but it's fine. You know, the video. We started Unit 9. We looked at okay, let's see about this unit. Sampling distribution shows every possible result a statistic can take. Oh my god. A sampling distribution shows every possible result a statistic can take in every possible sample from a population. And that's a pretty wordy way of saying it's a distribution for all possible values a sample can take. How often each result happens. Okay, that's fair. So something like can help us make and how. What am I doing? Okay, let's just get straight into it. We were on Unit 9. We looked through the different subjects. Okay, normal distributions, central limit theorem, biased, unbiased estimates, sampling distribution, sample proportion. That's just a different statistic that we can look at when dealing with samples. Okay, sampling distributions for differences in sample proportions. Okay, have we done this? I don't think so. Okay, we will go here.
We're told, suppose that 8% of all cars produced at plant A have a certain defect, and 6% of all cars produced at plant B have this defect. Each month, a quality control manager takes separate random samples of 200 of the over 3,000 cars produced from each plant. The manager looks at the difference between the proportions of cars with a defect in each sample. So they're looking at the difference of sample proportions every month. Describe the distribution of the difference of sample proportions in terms of its mean, standard deviation, and shape. So let's take these step by step. So first, let's think about the mean.
That's just we just minus these two. And then standard deviation is when we get the standard deviation, square root, no, square, add, that's sum, and then you square root.
Of our sample proportions. Pause this video and try to figure out what that's going to be. The sample proportion of plant A.
Yep, so that's going to be
Is just going to be the true population proportion for plant A. And they tell us that. They tell us that 8% of all cars, and we know what that means. What gets us a 2%.
yeah, okay.
Backing at this, the variance is.
What is the
So the
variance?
sample proportion from plant B. Some of you might be saying, wait, aren't we taking the difference of sample proportions here? Why are we adding?
Yes,
and the reminder is, remember, variance is a measure of spread. Spread we could take at each of our of plant. In the scenario that we are talking about, we didn't sample with replacement. We just took 200 at a time.
Yep, probability times 1 minus probability over sample size.
And times 1 minus.
What would this be? 200 over there, 8.92.
Minus the A, 1.92 is going to be just the square root of this. It's approximately equal to 0, the shape. So,
shape, standard deviation. Okay, I mean just shape. We already know standard deviation at this point. Shape.
Just as a review, we just have to remind ourselves.
All right, we just need to get the. We can assume this sample is normally distributed if both the expected value for successes, so the expected number of successes and fails, because these are Bernoulli random variables, can be classified as success or fail, are greater than 10. So 8% of 200 is 16, 92% is whatever that is, definitely higher than 16. So
that the
normal distribution, this is going to be normally distributed.
Distribution. Yep. 0.025, or it's approximately that.
And that makes sense because sample, and this is sample mean, sample standard deviation.
For plant B, 12 is different than this here. 0 is, maybe 0 is right over.
Shipment of, okay. He suspects that the confetti random sample of 20 of each kind of balloon, inflates them, looks at the difference, confetti irregular, between proportions of balloons that pop from each shipment. Okay. Could be that they're not independent. Wait, okay. So 0.25 times 8 AT. Whoops. Twenty times 420. I'm kind of sleepy. I just started this video, so I'm a bit sleepy, and I could fall asleep right now, but try and get some work done before I take a nap and keep doing math. 20 of each kind of balloon. Oh wait, we can't assume independence because this is more than because there's no replacement, and we're getting 20 of each kind of balloon. There's only 80 confetti balloons, so yeah, I'm pretty sure. Okay, that yeah. What are the mean and standard deviation of the sampling distribution of PA minus PB? Okay. Suppose that 60% of adults in District A support a new ballot measure, while 45% of adults in District B support that same measure. Pollsters take SRS from District A. 100. Okay. Okay, so the mean is just this and this. 0.15, okay. It's probably that. That looks right. That looks wrong. Asking them twice. They're not independent. I'm so confused. This is like so easy. This is making me question myself. Okay, next exercise. Shape of sampling distributions for differences in sample proportions. Okay. 8%, 5%. In plant B, we expect less than fewer defective cars. Yep. Suppose that 70% for the first time customers who order a vegetarian meal will order again. 65%. Let's, okay, 35%, 30%. Yeah, these are both fine. We expect 35 and 15, 30. Yep. Not normal because uh hmm in both orders, yeah. What will be the shape of the sampling distribution? 8%, 12%. The children. Okay.
In a previous video, we explored the sampling distribution that we got when we took the difference between sample proportions. And in that video, we described the distribution in terms of its mean, standard deviation, and shape. What we're going to do in this video is build on that example and try to answer a little bit more about it.
Okay, give me a sec.
So in this situation, what we want to do is find the probability, given that what we already know about this sampling distribution's mean and standard deviation and shape, we want to find the probability that the sample proportion of defects from plant B is greater than the sample proportion from plant A. So pause this video and see if you can figure this out.
We've already dealt with this in the last unit. You know, dealing with normal distributions and density curves and dealing with these kinds of problems. So essentially all we're being asked here is figure out the new distribution, find out the new mean, find out the new standard deviation, and find the area under the curve that suffices this condition. So probability that the sample proportion of defects from plant B is greater than sample proportion from plant A. It's similar to questions such as, here's an example. If there are two runners and they have mean time, if their run times have a mean of X and Y, and then standard deviation of A and B, I guess. Find the differences and find the probability that one guy is faster than the other. I don't know. And then it'd be a difference problem. And then you would be, let's say, if you're finding the times that runner A was slower than runner B, it might be the difference between runner A and runner B, so you go above. Okay.
Portion of the probability
that might have not
this
made a lot of
the
sense to you,
probability that
but
the
it makes a
sample
lot of
proportion
sense to me.
defects from
So
plant this is equivalent to the probability that the difference of the sample proportion is how many here so
yeah.
negative or
let's just watch the whole thing.
Is going to be negative. So this is equivalent to the probability that the difference of the sample proportions, so the sample proportion from A minus the sample proportion from B, is going to be less than 0. Or another way to think about it, that's going to be this area right over here. Now there's a bunch of ways that we can figure out this area, but the easiest, or one of the easiest, I guess there's many different ways to do it, is to figure out, well, how many, this is up to and including how many standard deviations below the mean, and then we could use a z-table. So what we just have to do is figure out what is the z value here. And the z value here, we just have to say, well, how many standard deviations below the mean is this? And I'll do it up here. Let me square this off so I don't make it too messy. Z is going to be equal to, so we are negative 0.02 from the mean, or we're 0.02 to the left of the mean, so I'll just do negative 0.02, and then over the standard deviation, which is 0.025, which is going to be equal to, get a calculator here, we get 0.02 divided by 0.025 is equal to that, and we are, of course, going to be to the left of the mean. So our z is going to be approximately negative 0.8 or 0.8. I'm saying approximately because this was approximate over here when we figured out the standard deviation.
What the heck is he doing?
It is negative 0.8. And then we just have to use a z lookup table.
Wait. Yeah, sure, okay.
Negative 0.8. And then we just have to use a z lookup table. And so if we look at a z lookup table, what we see here is if we're going to negative 0.8, negative 0.8 is right over here. So negative 0.8, and then we have zeros after that. So we're looking at this right over here. The area under the normal curve up to and including that z value. So we always have to make sure that we're looking at the right thing on this standard normal probabilities table right here. That gives us 0.21, or we could say this is approximately 21%. So let me get rid of this. And so we know that this right over here is approximately 21%. Or we could say 0.21. So the probability that the sample proportion of defects from plant B is greater than the sample proportion from plant A, it's, give or take, it's roughly 1 in 5.
That's pretty easy. Yep. So he figured out, he created a new distribution based on the problem, new sampling distribution. Easy money. Okay. 8 minutes. Okay, so we're looking at shape center variability, or shape mean variability, or shape center spread. Shape is determined by the shape of a sampling distribution p hat 1 minus p hat 2, and p hat just means sampling distribution, because I'm pretty sure p hat is probability 1, but sample probability. If we expect at least 10 successes and at least 10 failures, so what we do is we get the p hat value and we multiply that to the sample size. Successes and failures. Then this will be approximately normal because both of them are normal. And then if either of them fail, it means it's probably not normal. Or you can't assume normality. The mean difference is the difference between the population proportions. Okay. That's pretty easy, so just minus. And then variability, standard deviation. For each. This is similar to just variability for I don't know. This is exactly the same. Okay. So p times 1 minus p over n, and then you do that for both. And you get the square root of the sum to get the standard deviation. Okay. As long as you have two things. Okay. Independent observations between the two samples. Independent observations within each sample. So basically, they need to be independent between one another, and they need to be independent within each other. Okay. And then for standard deviation specifically, it matters, the 10% rule for normality matters. Or independence, not normality. Yuki is a candidate. Yuki is a candidate. Is running for office. Weird, okay. Okay. It's one of these two. I wish there was a drawing thingy. 40 and 40 and 45, so 0.45 times 0.55 divided by n is 100. Yep. You do the same thing, but for 0.4 times 0.6 times 100 divided by 100. Okay. You have square root of that. 0.07. This one. Okay. It's going to be approximately normal. 0.4, 140, and then 0.45, it's a bit higher. Keep, yep. That's standard deviation. That's mean. And so it's the difference between A to B. So, okay. What is the approximate probability that the percentage of voters who support Yuki are within 5 percentage points of each other? Okay, so we're getting the difference. So within 5 percentage points is positive or negative 5. So it's just between mm, percentage points. What the heck is a percentage point? Oh, right, okay, that still makes sense. 0.05, negative 0.05, and wait, 0, 50%. No. Okay, let's say this is 5%. What am I doing? Why is it wrong? Okay, I'm kind of stumped. Why? 0.07. Oh, yeah, whoops. Okay, back. 0.07. Oh my god. Where'd this even come from? I swear I copy pasted that. Okay. Inappropriate to use normal distribution. The sample size is 50, so each of these would fail the assumption for independence, standard deviation. Not standard deviation. Oh my god. I meant to assume that the combination that this PM minus PD, P hat M minus P hat D would be normal. Yep. 5% batteries at factory A, 5%, 90% of factory batteries factory B. SRS 250. Okay. Being asked to calculate the mean and standard deviation. So that would be, the difference is 4%. It's one of these. And it's always plus, even if it's difference. Okay, 15% of these students. Okay. So the true proportion is 15%. SRS 10%. Okay, let's give it a go. More than 10% of the sample would report that they experienced extreme levels of stress during the past month. Probability that P hat is 0.1. Okay. How do we do this one again? Okay. Let's not give up just yet. Nope. Yes, okay. Show calculator. Okay, let's fill in what we know. Above 0.1. The mean in the is 0.1. More than 10% of the sample would report. Okay, now I'm confused. How did we do this? Extreme levels of stress during the fast month. That's relevant. What am I reading? Trying to find the problem. Okay. We have a sampling distribution. 160 students. Oh, I think I know now. Okay, so the mean expected value is 10% of that. Need to know standard deviation. Need to know mean, mu. Sample proportion. Point 0.1 minus p over 160. So that's 0.09 times 160 equals 14.4. Or maybe I'm supposed to combine the two. Don't want to give up yet. Say it's 5%. It's 1 plus. It's, it's fucked up. Oh, wait. Ah, it's fucked up. Point 0.1. Point 0.1 is greater. Man. Whatever. Okay. Me. Ah. Fuck, that's stupid. Okay. Wait a minute. So, what? Oh man, I was overthinking. Okay, so this question is just asking to get the sampling distribution based on the parameters 15% of 1750, and then just find the probability that the sample shows zero point 0.1 or higher. My God, or higher than 0.1. Okay. Suppose that's 6%. Mm-hmm. 0.4 and 20. Mm-hmm. And then 0.45 and 100. Approximately normal. When there's shots. Okay, so it's one of these. What is that formula? I guess it's this, right? P times, yeah, NP. P times 1 minus P over N. Oh no. Nope, not that either. Okay, so the mu was... Let's try it again. 5 percentage points of the school board's 85% claim. This question is so confusing. I hate 5 percentage points. I wish they talked about fishes instead. I'm pretty sure it would be skewed to the right because we're only taking samples of 20. Oh, no, no, no. Okay, yeah. It's actually approximately normal because N is roughly 10%. No, it's not even 10%. Okay, it'd be skewed to the right. 20, 250, 8%, so skewed to the right. It's one of these. It's this one. No, this one, because that's N. Sampling size, sample size, sampling size. One of two. Why is it not appropriate for the researcher to use this formula for the standard deviation? Okay. 50% and 400, 40% and 500. I mean, they both pass the, was it 10 amount? Independence. Maybe it's this. It doesn't specify. Okay. We cannot assume independence for the students sampled from high school A. I missed this text. It's kind of hard to see. But 50%. What? Where's my freaking redo? What the hell? Well, that's kind of bullshit. Okay, let's try it one more time. 6 minutes. Where's the calculator button? 0.23, 250, 57.5. It's one of these. It's always plus. Oh, what am I doing? It's this one. No, always plus. Eh? 1 minus d. Oh, again. Oh my fucking lord. Is this one okay? 60 of the commercial burglaries. Mm-hmm. What will be the shape of the sampling distribution? Okay. Check these first. 300, 120, 180. Okay. It's 12 roughly. That's okay. Break. Okay, be back. What will be the shape? Minus, minus. Probably gonna be approximately normal. Okay, so 120 of 300. Oh, no, no. 120, 180, 35.41. Okay. zero point 0.3 times 1, 2. That's good. 0.41 times that. That's good. Okay, and then we expect that number looks right with low levels. Mm. Mm-hmm. What will be the shape? Okay, same shit. 87%, 90%. Huh? July, August. Okay, each month. 0.13. So it's too low. And 0.1 of 7 is also too low. young adults get jobs. What am I doing? I'm being distracted. Okay. E 60%. Okay, let's go. It's not. Yeah. Shape of the sampling distribution. Okay, we need to look at say failures and successes first. So 2%, 2%. Okay. Main office, branch office. 100 employees main office, 50% branch office. What's the shape? Okay. 1.5, 100%. That's too low. 2% branch office, that's too low. Okay. So both samples expect fewer than 10. Mm-hmm. Non-electric. Hold on. Have electric. Yeah, we expect fewer than 10 electric. Okay. Is this approximately normal or skewed? 200 cans. Mm-hmm. P hat with at least 3 cherries. So n is only equal to 3. And our mean is 98%. We don't know the standard deviation, that's fine. But we can't assume normality. And it's quite close to 1. So I'll assume that it's actually left skewed. What are the mean and standard deviation of the sampling distribution? Okay. 0.65. Because that's the parameter. And mm-hmm. And then n is equal to 100, so it'd be that. Because you're looking at sampling distribution, yep. Beatrice takes a simple random sample of 350. Mm-hmm. 12% of sample orders were returned. Okay. And then this is saying 9%, it is really 9%. Okay, so that's the parameter. So 9%, then 9, 0 0.9, 0 0.1 over n is 350. And then we're looking at this. Okay. Mean 0 0.09. Standard deviation is 350. Mm-hmm. You get square root of that. Yep, okay. And then we're looking for greater than 0 0.12, above 0 0.12. And I'm wrong again. More than 12% of the samples ordered would have been returned. Fuck, am I calculating things right? I'm wrong again. Oh, it's so annoying. Okay, 0 0.12. Oh my god. 0 0.5? No. Fuck! mu 0.09. This is equal to square root of that minus 1 over n, which is, oh fuck, am I supposed to use 5,000 or 350? 5,000. Oh, Jesus Christ. Okay. That's only where, okay. Oh, I also did the calculation wrong. Holy shit. Oh my god. Let's see. 0.024. Okay, let's answer. Samples aren't independent. They're not independent because you're selecting 50 and you only have 100, and they're in 6 colors. So even if it's just 2 colors, the 50-50 and yeah, that'd be a fucker. Okay. Yep, okay, next lesson. Oh god.
We've seen in the last several videos, you start off with any crazy distribution. It doesn't have to be crazy. It could be a nice normal distribution, but to really make the point that you don't have to have a normal distribution, I like to use crazy ones. So let's say you have some kind of crazy distribution that looks something like that. It could look like anything. So we've seen multiple times. You take samples from this crazy distribution.
Standard error. Take a sample from a population, calculate the mean of that sample, put everything back, and do it over and over. How much do those sample means tend to vary from the average sample mean? This is what the standard error of the mean measures.
We've seen in the last several videos. You start
Standard deviation of the sampling distribution of the sample mean.
off with any crazy
Okay.
distribution. It doesn't have to be crazy. It could be a nice normal distribution, but to really make the point that you don't have to have a normal distribution, I like to use crazy ones. So let's say you have some kind of crazy distribution that looks something like that. It could look like anything. So we've seen multiple times. You take samples from this crazy distribution. So let's say you were to take samples of, let's say n is equal to 10. So we take 10 instances of this random variable, average them out, and then plot our average. We plot our average, we get one instance there, we keep doing that, we do that again, we take 10 samples from this random variable, average them, plot them again, you plot again, and eventually you do this a gazillion times, in theory infinite number of times, and you're going to approach the sampling distribution of the sample mean. And our n equal 10 is not going to be a perfect normal distribution, but it's going to be close. It would be perfect only if n was infinity. But let's say we eventually, all of our samples, we keep, if we get a lot of averages that are there, that stacks up there, that stacks up there, and eventually we'll approach something that looks something like that. And we've seen from the last video that, one, if, let's say we were to do it again, and this time let's say that n is equal to 20. One, the distribution that we get is going to be more normal, and maybe in future videos we'll delve even deeper into things like kurtosis and skew, but it's going to be more normal, but
We
even
already
more importantly,
have.
or I guess even more obviously to us, and we saw that in the experiment, it's going to have a lower standard deviation. So they're all going to have the same mean. Let's say the mean here is, I don't know, let's say the mean here is 5. Then the mean here is also going to be 5. The mean of our sampling distribution of the sample mean is going to be 5. And it doesn't matter what our n is. If our n is 20, it's still going to be 5, but our standard deviation is going to be less than either of these scenarios. And we saw that just by experimenting. It might look like this. It's going to be more normal, but it's going to have a tighter standard deviation. So maybe it'll look like that. And if we did it with a even larger sample size, let me do that in a different color. If we did that with an even larger sample size, n is equal to 100, what we're going to get is something that fits the normal distribution even better. We take 100 instances of this random variable, average them, plot it. 100 instances of this random variable, average them, plot it. And we just keep doing that. If we keep doing that, what we're going to have is something that's even more normal than either of these. So it's going to be, a much closer fit to a true normal distribution, but even more obvious to the human eye. It's going to be even tighter, so it's going to be a very low standard deviation. It's going to look something like that. And I'll show you that on the simulation app in the next, or probably later in this video. So two things happen. As you increase your sample size for every time you do the average, two things are happening. You're becoming more normal, and your standard deviation is getting smaller. So that the question might arise, well, is there a formula? So if I know the standard deviation So this is my standard deviation of just my original probability density function. This is the mean of my original probability density function. So if I know the standard deviation, and I know n is going to change depending on how many samples I'm taking every time I do a sample mean. If I know my standard deviation, or maybe if I know my variance, right? The variance is just the standard deviation squared. If you don't remember that, you might want to review those videos. But if I know the variance of my original distribution, and if I know what my n is, how many samples I'm going to take every time before I average them in order to plot one thing in my sampling distribution of my sample mean, is there a way to predict what the mean of these distributions are? And so the standard deviation of these distributions. And so you don't get confused between that and that, and let me say the variance. If you know the variance, you can figure out the standard deviation. One is just the square root of the other. So this is the variance of our original distribution. Now, to show that this is the variance of our sampling distribution of our sample mean, we'll write it right here. This is the variance of our mean, of our sample mean. Remember, our true mean is this. That the Greek letter mu is your true mean. This is equal to the mean, while an x with a line over it means sample mean.
Oh my God. I've been getting that wrong. That's why I've been so confused.
Mean. So here what we're saying is this is the variance of our sample means. Now this is going to be a true distribution. This isn't an estimate. There's some, if we magically knew this distribution, there's some true variance here. And of course the mean, so this has a mean. This right here, we can just get our notation right. This is the mean of the sampling distribution of the sampling mean. So this is the mean of our means. It just happens to be the same thing. This is the mean of our sample means. It's going to be the same thing as that, especially if we do the trial over and over again. But anyway, the point of this video, is there any way to figure out this variance, given the variance of the original distribution and your n? And it turns out there is. And I'm not going to do a proof here. I really want to give you the intuition of it. And I think you already do have the sense that every trial you take, if you take 100, you're much more likely when you average those out to get close to the true mean than if you took an n of 2 or an n of 5. You're just very unlikely to be far away, right? If you took 100 trials as opposed to taking 5. So I think you know that in some way it should be inversely proportional to n. The larger your n, the smaller standard deviation. And it actually turns out it's about as simple as possible. It's one of those magical things about mathematics. And I'll prove it to you one day. I want to give you a working knowledge first. In statistics, I'm always struggling whether I should be formal and giving you rigorous proofs, but I've kind of come to the conclusion that it's more important to get the working knowledge first in statistics, and then later, once you've gotten all of that down, we can get into the real deep math of it and prove it to you. But I think experimental proofs are kind of all you need for right now, using those simulations to show that they're really true. So it turns out that the variance of your sampling distribution of your sample mean is equal to the variance of your original distribution, that guy right there, divided by n. That's all it is. So if this up here has a variance of, let's say this up here has a variance of 20. I'm just making that number up. Then let's say your n is 20. Then the variance of your sampling distribution of your sample mean for an n of 20, well, you're just going to take the variance up here, your variance is 20, divided by your n, 20. So here, your variance is going to be 20 divided by 20, which is equal to 1. This dividing distribution proofs are kind of, should be formal and giving you rigorous proofs, but I've kind of come to the conclusion that it's more important to get the working knowledge first in statistics, and then later, once you've gotten all of that down, we can get into the real deep math of it and prove it to you. But I think experimental proofs are kind of all you need for right now, using those simulations to show that they're really true. So it turns out that the variance of your sampling distribution of your sample mean is equal to the variance of your original distribution, that guy right there, divided by n. That's all it is. So if the variance of your original distribution, that guy right there, divided by n, that's all it is.
No way.
Is equal to the variance of your original distribution, that guy right there,
the variance of the mean of your mean?
Divided by n. That's all it is. So if this up here has a variance of, let's say this up here has a variance of 20. I'm just making that number up. Then let's say your n is 20. Then the variance of your sampling distribution of your sample mean for an n of 20, well, you're just going to take the variance up here, your variance is 20, divided by your n, 20. So here, your variance is going to be 20 divided by 20, which is equal to 1. This is the variance of your original probability distribution, and this is your n. What's your standard deviation going to be? What's going to be the square root of that?
So simple.
Standard deviation is going to be the square root of 1. Well, that's also going to be 1. So we could also write this. We could take the square root of both sides of this and say the standard deviation of the sampling distribution of the standard deviation of the sampling distribution of the sample mean. It's often called the standard deviation of the mean, and it's also called, I'm going to write this down, the standard error of the mean. Standard error of the mean. All of these things that I just mentioned, these all just mean the standard deviation of the sampling distribution of the sample mean. That's why this is confusing, because you use the word mean and sample over and over again. And if it confuses you, let me know. I'll do another video or pause and repeat it, whatever. But if we just take the square root of both sides, the standard error of the mean, or the standard deviation of the sampling distribution of the sample mean, is equal to the standard deviation of your original function, of your original probability density function, which could be very non-normal, divided by the square root of n. I just took the square root of both sides of this equation. I like to remember this, that the variance is just inversely proportional to n, and then I like to go back to this, because this is very simple in my head. You just take the variance divided by n. Oh, and if I want the standard deviation, I just take the square roots of both sides, and I get this formula. So here, the standard deviation, when n is 20, the standard deviation of the sampling distribution of the sample mean is going to be 1. Here, when n is 100, well, our variance here, when n is equal to 100, so our variance of the sampling mean of the sample distribution, or our variance of the mean, of the sample mean, we could say, is going to be equal to 20, this guy's variance, divided by n. So it equals, n is 100, so it equals 1/5. Now this guy's standard deviation or the standard deviation of the sampling distribution of the sample mean, or the standard error of the mean, is going to be the square root of that. So 1 over
I'm kind
the
of
square root of 5.
lost.
And so, this guy's I'll have you, a little bit under.
We take a sample, calculate the mean, put everything back. We have one mean. Do it again. Get another mean. Okay, so this is just the... Okay. How much do those sample means tend to vary from the average sample mean? Then we're going to end up with a distribution. And we're going to end up with an average.
Or 1/2 standard deviation, while this guy had a standard deviation of 1. So you see it's definitely thinner. Now I know what you're saying. Well, Sal, you just gave a formula. I don't necessarily believe you. Well, let's see if we can prove it to ourselves using the simulation. So I'll, just for fun, let me make I'll just mess with this distribution a little bit. So that's my new distribution. And let me take two things that's easy to take the square root of, because if we're looking at standard deviation. So let's take an n of 16 and an n of 25. And let's do 10,000 trials. So in this case, every one of the trials, we're going to take 16 samples from here, average them, plot it here, and then do a frequency plot. Here, we're going to do 25 at a time, and then average them. I'll do it once animated just to remember. So I'm taking 16 samples, plot it there. And I take 16 samples as described by this probability density function, or 25 now, plot it down here. Now, if I do that 10,000 times, what do I get? What do I get? All right, so here, just visually, you can tell just when n was larger, the standard deviation here is smaller. This is more squeezed together. But actually, let's write this stuff down. Let's see if I can remember it here. Here, n is, so in this random distribution I made, my standard deviation was 9.3. I'm going to remember these. Our standard deviation for the original thing was 9.3. And so standard deviation here was 2.3, and the standard deviation here is 1.87. Let's see if it conforms to our formula. So I'm going to take this off screen for a second, and I'm going to go back and do some mathematics. So I have this on my other screen so I can remember those numbers. So in the trial we just did, my wacky distribution had a standard deviation of 9.3. When n is equal to, let me do this in another color. When n was equal to 16, just doing the experiment, doing a bunch of trials and averaging and doing all the things, we got the standard deviation of the sampling distribution of the sample mean, or the standard error of the mean. We experimentally determined it to be 2.33. And then when n is equal to 25, we got the standard error of the mean being equal to 1.87. Let's see if it conforms to our formulas. So we know that the variance, or
I think it was...
we could almost say the distribution of your original distribution divided by the square root of n. So let's see if this works out for these two things. So if I were to take 9.3, so let me do this case. So 9.3 divided by the square root of 16, right? N is 16. So divided by the square root of 16, which is 4, what do I get? So 9.3, we wanted to do 4. It was after 10,000 trials. Maybe right after this, I'll see what happens.
Damn, okay. Another break. Pause. We're back. And, just give me 1 second. Whoops. Okay. Start. Get these two out, and I have 10 minutes
20,000 or
left for my
30,000 trials.
meeting,
We take samples of
so
16 and average them.
continue
now,
after.
Look at this. Here, we would take 9.3. So let me draw a little line here. Maybe scroll over. That might be better. So we take our standard.
He's just showing that it actually does work because of the simulation. So variance over n equals the standard deviation. Okay.
Deviation of our original distribution. So just that formula that we derived right here would tell us that our standard error should be equal to the standard deviation of our original distribution, 9.3, divided by the square root of n, divided by the square root of 25, right? 4 was just the square root of 16. So this is equal to 9.3 divided by 5, and let's see if it's 1.87. So let me get my calculator back. So if I take 9.3 divided by 5, what do I get? 1.86, which is very close to 1.87. So we got in this case 1.86. 1.86. So as you can see, what we got experimentally was almost exactly, and this was after 10,000 trials, of what you would expect. Let's do another 10,000. So you got another 10,000 trials. Well, we're still in the ballpark. We're not going to, maybe I can't hope to get the exact number, rounded or whatever. But as you can see, hopefully that'll be pretty satisfying to you, that the variance of the sampling distribution of the sample mean, the variance of the sampling distribution of the sampling mean, is just going to be equal to the variance of your original distribution, no matter how wacky that distribution might be, divided by your sample size, by the number of samples you take for every basket that you average, I guess is the best way to think about it. And sometimes this can get confusing because you are taking samples of averages based on samples. So when someone says sample size, you're like, is sample size the number of times I took averages, or the number?
This is like averageception.
number of things I'm taking averages of each time. And it doesn't hurt to clarify that. Normally when they talk about sample size, they're talking about n. And at least in my head, I think of the trials as you take a sample size of 16, you average it, that's one trial, and you plot it. Then you do it again, and you do another trial, and you do it over and over again. But anyway, hopefully this makes everything clear, and then you now also understand how to get to the standard error of the mean.
We're about to find out. Okay. N equals 16, mean weight 80, standard deviation 5. Suppose that each bag represents an SRS. Calculate the sample mean weight of each. Okay. Calculate. Wait, hold on. Mean weight of 80. Represents an SRS. $80 grams. So 80 and 5, and if that's X bar. I'm so bad today. Let's just fail so we can see. Okay. Okay. Whoa. Okay, so what were we doing? We were getting the standard deviation of the sampling distribution of the mean. Okay, what does the mean? The mean is average sum over sample size, sample sum over sample size. And we're getting the standard deviation of that. Oops.
The average male drinks 2 liters of water when active outdoors, with a standard deviation of
Okay, I need to go, and I'll be back in a bit for one more round of math. We're back. That was basically a break, so let's go 25 minutes and then close this video. Basically.
0.7 liters.
So
You are
cold.
planning a full day nature trip for 50 men. 50 men, and will bring 110 liters of water. What is the probability that you will run out of water? So let's think about what's happening here. So there's some distribution of how many liters the average man needs when they're active outdoors. And let me just draw an example. It might look something like this. So they're all going to need at least more than 0 liters. So this would be 0 liters over here. The
Standard error of the mean.
average male, so the mean of the amount of water a man needs when active outdoors is 2. The average male drinks 2 liters of water when active outdoors, with a standard deviation of 0.7 liters. You are planning a full day nature trip for 50 men. 50 men, and will bring 110 liters of water. What is the probability that you will run out of water? So let's think about what's happening here. So there's some distribution of how many liters the average man needs when they're active outdoors. And let me just draw an example. It might look something like this. So they're all going to need at least more than 0 liters. So this would be 0 liters over here. The average male, so the mean of the amount of water a man needs when active outdoors is 2 liters. So 2 liters would be right over here. So the mean is equal to 2 liters. It has a standard deviation of 0.7 liters or 0.7 liters. So the standard deviation, maybe I'll draw it this way. So this distribution, once again, we don't know whether it's a normal distribution or not. It could just be some type of crazy.
Average male, 2 liters of water when active outdoors. Standard deviation. Okay, so we got the mean. We got the standard deviation. Planning full day nature trip. Okay, and so our population is the whole male population. 50 men is our sample size. And we're bringing 110 liters of water. What is the probability that you will run out? Multiplication.
Distribution. So
Okay.
maybe some people need almost close to, well, everyone needs a little bit of water, but maybe some people need very, very little water. Then you have a lot of people who need that. Maybe some people who need more, and maybe no one can drink more than, maybe this is like 4 liters of water. So maybe this is the actual distribution, and then one standard deviation is going to be 0.7 liters away. So this is 1.7 liters is, so this would be 1 liter, 2 liters, 3 liters. So one standard deviation is going to be about that far away from the mean. If you go above it, it'll be about that far if you go below it. So let me draw. This is the standard deviation. That right there is the standard deviation to the right. That's the standard deviation to the left. And we know that the standard deviation is equal to, I'll write the 0 in front, 0.7 liters. So that's the actual distribution of how much water the average man needs when active. Now, what's interesting about this problem, we are planning a full day nature trip for 50 men and will bring 110 liters of water. What is the probability that you will run out? So the probability that you will run out, let me write this down. The probability that I will, or
The probability that you will run out, it would mean that the average sample mean is 2.2, right? 2.2 times 50, 110.
that
So
you will run out is equal or is the same thing as the probability that we use more than 110 liters, use more than 110 liters on our outdoor nature day, whatever we're doing, which is the same thing as the probability. If we use more than 110 liters, that means that on average, because we
Greater
have
than
50 men, so
2.2.
110 divided by 50 is what? That's 2 point. Let me get the calculator out just so we don't make any. That the this sample are different. Let's say that this is the frequency, and then of it's going to plot them all out. We sample mean. So you take 50 people, find their mean, plot the frequency. 50 people find the mean. This is actually going to be a normal distribution, regardless of, this one just has a well-defined standard deviation. I mean, it's not normal. Even though this one isn't normal, this one over here will be, and we've seen it in multiple videos already. So this is going to be a normal distribution, and the standard deviation, and we saw this in the last video, and we hopefully we've got a little bit of intuition for why this is true. The standard deviation, actually, maybe put it a better way, the variance of the sample mean is going to be the variance. So remember, it's going to be, this is standard deviation. So it's going to be the variance of the population divided by n. And if you wanted the standard deviation of,
So this is basically getting just the standard deviation of a sampling distribution. My God. Standard error of the mean. No way. Wait, standard error of the mean. Standard error of the mean, literally standard deviation. No way. Standard error, standard deviation. Measures mean precision, measures data dispersion. Okay. If you take a sample from a population, you get two main statistics from it, the mean and the deviation. One describes the center, one describes the shred. Imagine you kept drawing new samples again and again. The deviation is the standard error. But Shao said in a different video that the full name was the standard... Maybe the standard error of the standard... Okay.
the
Whatever.
standard deviation of the sample mean is going to be equal to, square root of this side over here, is going to be equal to the standard deviation of the population divided by the square root of n. And what's this going to be in our case? We know what the standard deviation of the population is. It is 0.7, 0.7, 0.7. And what is n? We have 50 men, so 0.7 over the square root of 50. Now let's figure out what that is with the calculator. So we have 0.7 divided by the square root of 8 was pretty close to 0.99. So I'll just write that down. So this is equal to 0. So this is going to, which is going to be our 0.1. So for deviations above the mean, we are 0.0.
Okay, I think. Do I want to skip? Or do I want to just keep watching? No, I'll keep
average,
watching.
that our sample will have an average greater than 2.2. So this is the distribution of all of the possible samples, the means of all of the possible samples.
Okay, so we had the mean.
Now, to be greater than 2.2, 2.2 is going to be right around here. 2.2
and these are both
is going to be right around here. So we essentially are asking, we will run out if our sample mean
we had an average,
falls into this bucket over here. So
we got another average.
What is, you can even view it as, what's this area under this curve there. And to figure that out, we just have to figure out how many standard deviations above the mean we are, which is going to be our z-score, and then we could use a z-table to figure out what this area right over here is. So if we are, so we want to know when we are above 2.2 liters. So 2.2 liters, 2.2, we could even do it in our head. 2.2 liters is what we care about. That's right over here. That is, our mean is 2. So we are 0.2 above the mean, above the mean, above the mean. And if we want that in terms of standard deviations, we just divide this by the standard deviation of this distribution over here. And we figured out what that is. The standard deviation of this distribution is 0.099. So if we take, and you'll see a formula where you take this value minus the mean and divide by the standard deviation. That's all we're doing. We're just figuring out how many standard deviations above the mean we are. So you just take this number right over here, divided by the standard deviation, so 0.099 or 0.099. And then we get, let's get our calculator. And actually we have the exact number over here. So we could just take 0.2. We could just take this 0.2 divided by this value over here. And on this calculator, when I press second answer, it just means the last answer. So I'm taking 0.2 divided by this value over there, and I get 2.020. So that means that this value, or actually, right, this probability is the same probability of being 2.02 standard deviations, or maybe I should write it this way, more than, let me write it down here where I have more space. So this all boils down to, the probability of running out of water is the probability that the sample mean will be more than just the 50 that we happen to select. Remember, if we take a bunch of samples of 50 and plot all of them, we'll get this whole distribution. But the 150, the group of 50 that we happen to select, the probability of running out of water is the same thing as the probability of the mean of those people will be more than 2.020 standard deviations above the mean of this distribution, which is actually the same the same distribution. So what is that going to be? And here we just have to look up our z table. Remember, this 2.02 is just this value right here, 0.2 divided by 0.09. I just have to pause the video because there's some type of fighter jet outside or something. Anyway, hopefully they won't come back. But anyway, so we need to figure out the probability that the sample mean will be more than 2.02 standard deviations above the mean. And to figure that out, we go to a z-table, and you can find this pretty much anywhere. Usually it's in any stat book or on the internet, wherever. And so essentially we want to know the probability. The z-table will tell you how much area is below this value. So if you go to z of 2.02, that was the value that we were dealing with, right? You have 2.02. It was, so you go for the first digit. We go to 2.0, and it was 2.0, 2.02. 2.02 is right over there, right? So we had 3. Let me write it down over here. This 0.9783, we have answer just right here, 2.17.
I just realized my mic's been off this whole time. I've been raging a bit. Not really. Probability that the mean delivers farther than 2 minutes from the population mean. Oh, it's not. Okay. We got this. $250 and the standard error of the mean is gonna be 8. Wait. Strongly skewed to the left. Management takes a random sample of 64 of these pizzas. Assume that the samples are independent. Okay. So it's independent, so we can assume that it is going to be normally distributed. 4, 8, like that. So 250, yeah. 1 in between. Within 1 gram. Okay. Between 250, 249, and 251.68. Next article. Here's a type of problem you might see on the AP statistics exam where you have to use a sampling distribution of a sample mean. Okay. Time check. An automaker does quality control tests in the paint thickness at different points on its car parts since there is some variability in the painting process. A certain part has a target thickness of 2 mm. Yep. Mean standard deviation. We're given a sample size. Assuming the stated mean probability that the mean thickness in sample is it. Can we assume that it's independent? Can we assume that it's going to be normally distributed? Okay. A 100. Sample mean thickness. Skewed to the right. Or is that approximately normal? Explain. Since n equals, okay, fine. So that's not 100 samples, that's n equals 100. Okay. Find the mean and standard deviation of the sampling distribution. What is the mean? 2 mm. What is standard deviation? 0.5 mm. No, it's actually going to be 0.5 divided by square root of 100. So it's 0.5, 10, 0.05. Assuming the stated mean standard deviation of the thicknesses are correct, what is the approximate probability that the mean thickness in a sample of 100 points is within 0.1 mm of the target value? Sure, okay. And then it says within 0.1, okay. 0.95, less than 7. Okay.
What we're going to do in this video is explore the sampling distribution for a difference in sample means. And we'll use this example right over here. So it tells us a large bakery makes thousands of cupcakes daily in 2 shifts, shift A and shift B. Suppose that, on average, cupcakes from shift A weigh 130 grams with a standard deviation of 4 grams. For shift B, the mean and standard deviation are 125 grams and 3 grams, respectively. Assume independence between shifts. Every day, the bakery takes a simple
Sampling distributions for differences in sample means. Okay. Large bakery. Shift A, shift B. This is what we're going to compare. So we're going to be given a. Oh, okay. Average weight, standard deviation. Average weight, standard deviation. They're independent, so that's okay. Every day, the bakery takes 40 cupcakes from each. Okay. Calculate the mean for each sample, then look at the difference. Okay. So find the probability that the mean weights from the samples are more than 6 grams apart. Okay. So we're going to have a sampling distribution of the difference in sample means. How much time do we have left? Still over 7 minutes. Okay. Short break and then continue. Okay, let's finish
random
this
sample
off.
of 40 cupcakes from each
We'll just
shift.
watch the
They
video
calculate the mean weight for each sample.
and here.
Then look at the difference, A minus B, between the
But
sample means.
basically, we are gonna take the difference. No, we're gonna. So first thing, establish independence. Are they normally distributed? And then you get the mean and the standard deviation of the difference distribution.
Find the probability that the mean weights from the samples are more than 6
And then it says find the area under the curve.
grams apart from each other. So I'm actually not going to tell you immediately to pause this video and try to work through this on your own. First, I'm going to think about how we could break this down, and then I'll ask you to pause and try to tackle each of those parts by itself. So in order to tackle this eventual question, we're going to have to think about the mean of the sampling distribution for the difference in sample means. So sample mean from group A minus sample mean for group B. We're going to have to think about the standard deviation of the sampling distribution for the difference in sample means. And we're going to have to think about, is this distribution normal? If we're able to figure out these 3 things, then we just have to figure out, well, how many standard deviations away from the mean is this? And we could use your standard z-table to figure out the probability. So now I encourage you to pause this video and try to tackle this first part. What is the mean of the sampling distribution for the difference in sample means? All right, now let's work through this together. So the mean of the sampling distribution for the difference in sample means, and we have seen this before, this is going to be equal to the difference between the means of the sampling distribution for each of the sample means. So that mean minus this mean. And we also know that
this is going to be so mu of x bar, the average. That's so much average-ception. Okay, the average of A, the sampling average of A, and the sampling average of B will be equal to this. So you just get the values and you minus them. So you go A 130, B 125, so it's gonna be 5.
So have deviation. So we know that the variance of
Okay. And then the variance of the standard deviation of the sampling distribution of a mean is equal to the standard deviation over square root of n. But in this case, I think we would do the variance. So instead of square root, it would be outside, maybe.
The sampling distribution for the difference in sample means, assuming that your two samples are independent and you're sampling with replacement. If you're sampling with replacement, it's actually going to be the sum of the variances of the sampling distribution for each of the sample means. So it's going to be that plus this right over here.
And then you
Now
square
you
root.
might be saying, wait, we're not sampling with replacement. Well, we also know that if each of the sample sizes are less than 10% of the population, then the difference is negligible. And so we could still use this formula. And so you can see that the simple random sample here is 40 from each shift. And they say that a large bakery makes thousands of cupcakes daily in 2 shifts. So even if it was 1,000, 10% of that would be 100. This is less than 10%. So we meet that condition. So we can use the same formula that you would use if you were sampling with replacement. This is your sample size. And
Okay,
then
so that's how you do it.
this over here is going to
You
be the
get
same
them
thing
two and
for
then you
shift
just
B.
add them.
The standard deviation could write in
And
each case standard deviation, the population grams squared. A gram squared is kind of, and so this is going to be equal to, let's see, 16 plus 8. Now tells us what the standard deviation is going to be, because of course the units are back to grams, which makes sense. And this is approximately going to be equal to, get my calculator out, 5 divided by 8 equals 0 is. And so I encourage you to pause the video again and think about that. Each of the later this.
Okay, let's try. Let's go. It is so freaking cold. I need to close the window, but I don't want it to be stuffy. Okay. What are the mean standard deviation? Okay, so mean 22, 20. Okay, so 2 automatically. It's one of these two. And then it should be this. So standard deviation of A, standard deviation of B over the sample size of A as sample size of B, and then square root 7 squared, 6 squared, 49. Yep. Why is it not appropriate to use this formula for the standard deviation of this? Okay. Okay, let's go back to the very basics. So, establish independence. Okay. Request books, pick up their books, have them delivered. Here's the historical data. Society leader take separate 24 samples, look at the difference. Okay. They're not independent. Wait, pick up location. I think that makes sense, right? It's still the same library. Hmm. Okay, well, it has to be the home. Home because freaking size, sample size. Okay. Next, 6 and 57, 54, so 3. One of these two. Error. Something over the square root of n. This? I think it might be that. It's this. Okay, so we're almost done with Unit 9, that's fine. I think we started Unit 9 in the last video. So, I'm just gonna end this over here. So let's quickly review what we've actually went through in this video. Unit 9, okay, so last video we did normal distribution, central limit theorem, biased, unbiased point estimates, talking about independence, talking about sampling distributions, talking about statistics, talking about normality, independence, assumptions for these two things. Sampling distributions for sample proportions. Okay, we talked about sample proportions. We talked about mm, what did we talk about? Normal conditions. Okay. A lot of these things are very similar, very related, so it's hard to compartmentalize and keep things separate, you know. Whereas if I was learning calculus and I was learning statistics, it's very easy to remember, okay, in calculus I did this, in statistics I did this. A lot of the operations we're doing carry over from previous modules or previous units, so yeah, okay. And then we did sampling distributions for differences in sample proportions, okay. And a lot of these things just involve looking for areas under a curve, finding a mean, finding a standard deviation, combining them, doing operations, identifying what part of the curve are we trying to find the area of, sampling distributions for sample means, sampling distributions for differences in sample means, and these are quite similar. So, sampling distributions for sample means, you have a population, you get an average, and then you get an average of the average. And also okay. Sounds kind of stupid, but that's kind of what it is. It's used for answering questions like, hmm, standard error, standard error of the mean. Let's just quickly review it one last time.
Divided by the square root of n. I just took the square root multiplication of
Well,
the
let's just look
sampling
it up.
distribution of the sample mean.
Basically, the standard deviation of the derived normal distribution. Derived from where? So you get a bunch of averages, and then you get the average of that. No, and then you get the standard deviation of that. No, oh my god. Nope. Sampling distributions, okay. Begin. Let's say we have a something like this. N equals 10, not 16, n equals 25. And then if we do 10,000, 10,000, maybe mean as well. And we do that 10,000 times. And then, how do I stop that? That's fine, okay. Original standard deviation is 7.97. N equals 16. The mean was 16.69. These are both very close. So 16.69 square root of 16 is 4 equals 4.1. Wait, what am I doing? Oh, 7 7.97 square root of 16.4. 1.999 standard deviation. Okay. So basically what the standard error is literally just a standard deviation of a sampling distribution. Oh my god. Took me ages to get that. Okay. Well, I think that's perfect way to end the video. Um, if you made it all the way here, I just want to say thank you. Leave a like, leave a subscribe, comment down below if you have anything interesting to say, and I'll see you in the next video. Bye bye.